Thank you very much. So I'm talking about service discovery and in the context of Node.js microservices. And this is the put up your hand question. How many of you guys are doing Node.js microservices? Cool, okay, so this should hopefully give you some interesting ideas about some of the approaches that my company Nearform has taken. This talk is, it's not really telling you how to do things. It's more, here's the history and the story that we went on with Node and microservices, and this is kind of one of the places that we've ended up. And we've used a whole bunch of different service discovery mechanisms, and they all have downsides. But we like to think that we've kind of found an approach which is really, really nice, which is what I'm going to talk about today. But first, a little bit of philosophy. This is the flight deck of the Space Shuttle Atlantis. The cool thing about the Space Shuttle is the flight software is some of the most perfect software ever written. It's about 400,000 lines of code. They had something like one bug per release. And each line of code cost $1,000. And it's pretty much as close as humanity has ever come to software that is just without any flaws. But the reason I have it up here is that the big problem that we see in enterprise software development, and that is a theme now in Node and the story of Node, because we've won, because Node adoption has taken off in a really, really big way, lots and lots of big companies are using Node. And Node is exposed to the same flaws that all of the older platforms, Java and .NET, etc., also were exposed to. Enterprise software development is predicated on building software that is this perfect. There's an implicit assumption that you have to be this good. You're not allowed to have any bugs. Now, whether you have a software development methodology or a bug tracking system or whatever, that implicit assumption is still there. And the problem with that is that it creates so many layers of bureaucracy and so many layers of process and management and so much fear that it's really difficult to move very fast. So although this is beautiful software, if we don't learn from the mistakes of the past, all of our Node applications end up trying to emulate this, and we end up in the same place as we did before, where we can't build software really, really fast. There's a different vehicle, a different aircraft, which I think is more inspirational. This is the Gossamer Albatross. It's the first human-powered airplane. The first human-powered airplane to fly across the English Channel. So it was built to win a kind of an X Prize. £100,000 sterling was offered in 1959 for the first person to fly under their own power across the English Channel, which is only a couple of miles. But it took 20 years before this aircraft was built. And a lot of engineering teams took up this challenge, and they'd spend a year designing something, and then they'd build it. And then whoever the pilot was would pedal frantically for a couple of hundred yards and then crash, either because the airplane fell to bits or they were exhausted. And the engineer who eventually solved the problem, a guy called Paul McCready, realized that the problem wasn't flying across the English Channel. The problem was being able to iterate on the design of the aircraft so that you could quickly fix problems. So he came up with a system of aluminum piping and Kevlar and wires that let him build sometimes 3 different aircraft designs a day. And once that system was in place, it only took a year to win the prize. And I feel, and our experience with Node is that Node is this empowering. Node lets you build and iterate really, really quickly. And the Node module system in particular is something that we've seen as being a key element of that. But one of the challenges that you get in larger scale enterprise development is that the Node module system, while it's really great as a component model at the infrastructure layer, for building things like authentication systems or templating systems or stuff like that, is not so great as a component system at the business logic layer. And we ended up moving towards a model where microservices become that component model. But that then engenders all of the other questions about how you run and manage microservices and how those components talk to each other. But let's not forget the problem that we're trying to solve here. Because Node has now seen this wonderful adoption, and if you saw Michael Rogers' keynote, you see all these wonderful, huge numbers. We are in grave danger. Node development is in grave danger of ending up like this. So this is a yak in the Himalayas. Enterprise development is like this. You want to do something, and you end up having to do a series of increasingly small, frustrating things that end up with having to shave a yak in the Himalayas to get anything done. This is the place that Node is going if we don't do something about it, if we don't adopt a method of building software that is joyful. And this is what we want enterprise software to be like. Right? I love this picture. Right? This is an ad for Legos from 1981, I think. Right? And this is why we became software developers in the first place, right? To feel this way. But the nice thing that this symbolizes is the Legos are components that you can put together. You can compose them in different ways. And it's that composability that is the key thing that makes components work. And composability is something it's quite difficult to achieve because the way that components talk to each other very much determines how composable they are. So yes, Node modules are fantastic. But if you think about it, they're not very composable. Node streams are extremely composable because you can put them together and you can pipe between streams. Unix pipes are another great example. But a generic Node module has a complex API of function calls and objects or whatever, and it's difficult to fit them all together. And without composability, you don't have a really strong component model for dealing with business logic. And you need that for dealing with business logic because business logic is difficult to predict. Things change over time. And especially when you want to move to a world where you can do continuous delivery and you can build features in the morning and deploy them in the afternoon and get all that wonderful good stuff and fulfill the goals of the digital transformation project you're working on and all that sort of stuff. And that's where we found that microservices come in for us for Node. They have three key kind of properties. They're small independent processes. That independence means you can deploy them independently, which is the important thing. They're communicating via messages. And I think it's important to realize that level of abstraction means it doesn't matter if they're REST calls or using a message bus or something else. It's the message-oriented nature of the communication that's important. And that's something that we can build on. And then microservices, like I've said, are this powerful component model. Because if you put them together in the right way, if you allow them to communicate in the right way, you get composability. And then you get all these wonderful benefits, like avoiding technical debt because they never get very big, and you avoid complex data structures. You get continuous delivery because you start using Docker and Kubernetes and all that good stuff. And then you can build quickly. And you can build quickly because you can compose them together. And I'm sure a lot of you, if you've been using microservices, are also familiar with some of the trade-offs, right? Deployment is definitely way more complicated. And it does have this weird programming model. The last speaker was showing traces of flows through microservice systems. You not only have to understand the microservice that you're working with, but you also have to understand these message flows. So we use things like Zipkin and stuff like that to kind of understand how they fit together. But it is the nature of this type of system that you have to think at a level above your programming language. So it's not just how do Node modules communicate with callbacks or promises or streams. You also have to think about these message flows and how they fit together. And then, how do they find each other? How does one service find another service? Which is a much, much deeper problem and a much trickier problem to solve than deployment, which is essentially just getting to know and use the right tools. So if you've done a computer science degree, after 3 or 4 years of study, you end up being able to do this. And this is the final result of studying computer science. You get to draw two boxes that communicate with each other. This is the essential representation of two components communicating. Component A needs B to do something, and it sends B a message. And this could be an object, or it could be microservices, or it could be two node modules, or whatever. The problem here is the coupling between A and B. Because whatever these things are, even if they're two microservices, if one microservice makes a REST call to the other microservice, well, it has to know its location on the network. And that's a coupling. It's a really, really tight coupling. Somehow A has to know about B. Somehow A has to know the identity of B. And that's the core weakness, because if you just blindly follow through on a REST-based model and you build loads of microservices, you end up with a distributed monolith. There is no essential difference logically between one object instance calling another object instance and all the issues of dependency injection and design patterns, and one process on the network calling another process on the network, because you still depend on this notion of identity. You still have this coupling. This is the world that we want. We want a world where A sends out a message and it doesn't know who implements the other side of the message, who does the action. And B receives messages, but it doesn't know who it's receiving them from. And now you have decoupling, and now you can change A or deploy multiple instances of A and do the same with B. This is the world that we want to get to. This is sort of the promised land. This is the power that microservices is supposed to give us, but if in your microservices you're doing HTTP REST calls, you don't get this. You get tight coupling and you end up with a mess. A lot of people have ended up in that place. We've done it ourselves. So as I said, this is sort of a story. We've made all these mistakes as well. So how can you do service discovery, right? A has to send a message to B, but it has to know where B is. And if B has a strong identity for A, if it's a specific network location, that's bad. So can you reduce the strength of the coupling? There's different ways, different approaches you can take to service discovery. We've done all of these. Some are worse than others for coupling. So you can bake in configuration into Docker images. Everything is immutable. You can have intelligent load balancing. And that one works quite nicely, right? So instead of talking to a specific microservice, you're talking to load balancers. Maybe they're agents on each box. But there's all sorts of different ways you can play that one. You can have service registries, right? So who's using a service registry? Not too, okay, wow, okay, service registries don't work in production. Yeah, we've discovered that one as well, right? There's all sorts of weird race conditions. You can use DNS, right? So Kubernetes, there's all sorts of different ways you can play around with DNS as well. Or use a message bus. So it gives you a certain amount of decoupling. All of these things, to a certain degree, still preserve the notion of identity. So even a message bus, even the topic of a message bus is still a notion of identity. So you have to ask the question, is that inherent? Is service identity something that you just can't get away from? Is it possible to have this world where services can talk to each other without knowing the identity, the location of another service? Now let's return to the notion of components. There's this book called 507 Mechanical Movements, which has been digitized. And there's a website. You check it out on Google. Some of these are animated, which I find, again, really inspirational because these are mechanical components, but they're based on physical principles. And if you can identify some principles that let you get components talking to each other, then you can move forward. And in the years that we've been working on this stuff, we've kind of identified two key principles. One of them is pattern matching, and the other is transport independence. Transport independence is simply, it shouldn't matter whether it's a message bus or REST or whatever. The mechanism whereby a message gets from one place to another should not matter. So in your code, you need to have some sort of abstraction layer that abstracts that away, so that you aren't making a decision, we must use REST. To make that decision is to jump ahead too far. Pattern matching is how you get away from this notion of identity. You send out a message, and the microservices that care about it should respond. In an idealized world, every microservice sees every message and then decides to respond to the messages that it cares about. And that obviously doesn't work in practice, which is where we come into using some interesting algorithms to solve this problem. In practice, this is what it looks like conceptually, right? Microservice A is sending out a message, let's call it the King of Hearts, and microservice B listens for heart cards. It listens to the heart suit, which means that whatever heart card that A sends out, B will respond to it. It's just a kind of a conceptual metaphor. This is the way that pattern matching works. If I send out a user login message, it doesn't matter what type of user it is, an employee or a contractor or a manager, the login service recognizes that it's a login message because of certain properties of that message. It doesn't matter what they are. It doesn't matter what the pattern matching algorithm is. Simply the fact that you're looking at messages and matching on the patterns is what counts. And this gives you blind messages. Services can then have zero knowledge of other services using this pattern matching approach. But to make this work in practice, you need to use a peer-to-peer approach. And there's multiple different ways of doing this. I mean, you can have a complete broadcast of all the information to every microservice. That doesn't scale. But because people have been trying to solve that problem, a couple of interesting algorithms have arisen. This is the one that we use. Scalable, weakly consistent, infection-style process group membership. And it's actually used by Uber. And it works in a very, very interesting way. Every microservice pings a random subset of every other microservice to see is it alive. So you can tell very quickly if a service is dead. You don't need to use heartbeats. Piggybacking on the health checks is information about new microservices that join. So when the pink microservice joins, information that it has joined disseminates very quickly throughout the network. And that gives you a model that looks like this. Communication between A and B happens through a small abstraction layer, which implements this algorithm, which means you can send out messages and you don't know who you're sending them to, but they end up in the right place, which gives you some very powerful component patterns. For example, if you wanted to scale, you just add new instances of B, and your little abstraction layer can round robin between them. If you want to do things like pub sub, well, I can add other microservices that do other things that also listen for these patterns. Again, it's very, very simple to implement that in the abstraction layer. You don't need any extra infrastructure. As part of my component model, I can do things like moving from a general implementation to a specific one. I can progressively add features to my system. In this case, B was the first microservice I wrote, but then I have C, which handles the ACE cards. It's a special case. So I add features to my system by adding new microservices. And finally, you get composability. A was talking to B originally, but then I can inject C in the middle of that conversation, and C can do caching, or it can add a permissions check or auditing or something like that. A still thinks it's talking to B, but now C has added a layer above that business logic. And this is where you get composability. And I believe I'm now just exactly out of time. So if you want to see this in a node context, if you want to see an actual system and code and how this fits together, we've written a little Twitter clone in about 14 microservices that uses these ideas, pattern matching and transport independence, and the composability, so that you can see in code what this stuff actually looks like. And I'm also writing a book on all of this stuff if you want to talk about more of the conceptual stuff and that sort of thing. Thank you very much.
We actually have time for one question. Does anybody have a question? Raise your hand. Oh, in the back.
My question is, how do you handle like multiple people responding to that? I guess if I'm saying start an upload or whatever, who takes ownership of that?
Okay, so in a request response model where A is expecting a response, that's up to A. So A could just take the first response say, I'm done, and ignore everything else. Or in other models, they can say, OK, I've got 5 responses, now I'm going to rank them, or maybe use the best one. But it's up to A.
Great, thank you. If
Okay,
you have more
thanks,
questions, another thank you. Give them a round of applause.